Hello, it's Dr. Huan again. We are talking about section 4.8, homework problem number 4. In this problem, there is a proposed proof for this statement, and this statement is saying for every integer n, if n is greater than 2, what happened? Then we can conclude that there is a prime number p such that p is in between n and n factorial. Now let's take a look at the proof. It's first one says let n be an integer that is greater than 2. Seems like that's exactly the assumption. And by the infinitude of the primes theorem, which is theorem 4.8.4, this theorem is saying that there are infinitely many primes out there. So because there are infinitely many primes, for any number n, you can always find a prime that is greater than n. So I see no problem from, at least this statement is not wrong. So I'm going to continue to read. Since n is greater than 2, n factorial minus 1 is an integer that is greater than 1. Now n is greater than 2 right there. That means n is at least 3. 3 factorial, which is 6. 6 minus 1 is 5. So therefore, this is, and for sure, is an integer that is greater than 1. That's true. So no problem with this statement. So by the divisibility by a prime theorem, the theorem 4.4.4 says for any number that is for any integer that is greater than 1, you can always find a prime divisor. There's always a prime that divides an integer that is above 1. So because this n factorial minus 1 is already greater than 1, n factorial minus 1, so therefore according to this theorem, there exists at least one prime p, so that p divides this number. So this is completely fine. Now, thus, m factorial minus 1 is, p is less than or equal to n factorial minus 1. I have no problem with this one because when p divides n factorial minus 1, that automatically means p less than or equal to n factorial minus 1 by one of the results from the book. So this is completely fine, okay? And obviously, n factorial is greater than n factorial minus 1. So basically, this means this. This is less than n factorial. So this is 1 less than n factorial. So certainly it's less than n factorial. So therefore, p is less than n factorial. So this is completely fine. This is coming from this statement. I do not see any error. Now, therefore, by step 2 and 5, there is a prime number p. So let's continue, go back to look at 2. So 2 says when you have an n, you can always find a p. There exists a p, okay, at least one prime. Now, of course, there are infinitely many primes that will be greater than n. We're just saying at least one, and then it just labels p. And now, in number 5, actually number 4, this p has to be very specific. There's a p, not all the prime p, but there's some specific p that divides n factorial minus 1. Now, compared to step 2, this p is pretty generic, pretty general. For instance, give me any integer n, say suppose 6, right? We can always find a whole bunch of primes that will be greater than this particular n. For instance, 7, for instance, 11, for instance, 13, 19, and so on and so forth. So here this p is a generic prime that's been quoted. Now, instead of this p, if you say you have a 6 factorial minus 1, and we guarantee there's some p that divides this guy, but this p has to be very specific. There may be one, there may be two. I know there's at least one, but this p is not a generic p. So here I do see a problem here. This saying by step 2 and 5, there is a prime number p such that p is in between n and n factorial. For this one is general, but for this one is very specific, so they may not be the same p. That's the problem. So here I actually read through all of them. Let's take a look at the proof. Does not work if n is prime. This will work if n is any number above. So I'm not gonna quote this as an error. This is a pretty obvious error here. The step 2 and step 5, they may not refer to the same p. They may not use the same p. All these are justified. We kind of go through all those. And the statement can only be proved by contradiction. I do feel like if you do not prove using a contradiction, there's no way that you can. So for any number, there were infinitely many number n that is greater than 2. You are not able to find, use as a proof method. It's not realistic that you can find a prime number so that it's in between these two. So to me, the proof actually will be done by contradiction. So that's the how I would identify which one is incorrect. Now, to be like completing this proof, if you would like to hear what I would like to say for this proof, actually here's what I would do. So I'm gonna rearrange a few things. This is something because it's generic p. This is not actually useful. Okay, I will use all the other steps from 1, 3, 4, 5, but not the 6 because 6 is messing up 2 and 5. So I'm not gonna use that. So here's what I would add after that. I would say now we do have p is divides n factorial minus 1, and also we establish p is strictly less than n factorial. Okay, strictly less than n factorial. Now p. So now the next step, I'm gonna label this the next step. I'll just use a bullet point. So in this case, let's discuss p is either so p is either I'm gonna, instead of using words, I'm gonna say p is either less than or equal to n, or p is greater than n. So p divides n factorial is these two cases. So it's either less than or equal to n or greater than n. Okay. Now let's discuss if p less than or equal to n, then p for sure divides n factorial, because what is n factorial? N times n minus 1 times n minus 2 and so on and so forth all the way down to 1. And because p less than or equal to n, then p must be one of those numbers, right? So this n factorial is n times n minus 1 times n minus 2 and so on and so forth, down to 3 times 2 times 1. So p would be one of the integer here, so p certainly divides n factorial. Now when p divides n factorial, now since p divides n factorial and p divides n minus 1 factorial, okay, then if you look at the book, the proposition 4.4. Let me quickly quote the proposition from the book, which is 4.8.3. I'm sorry, proposition 4.8.3, which says if for any integer a and any prime p, if p p divides a, then p does not, if p divides a, then p does not divide a plus 1. Okay, now obviously this will contradict to this proposition. Why? Take a look at here. P divides hang on, sorry, let me quote it carefully again. Okay, sorry, I quoted incorrect earlier, so a little mistake here. We say p divides n factorial minus 1. I'm sorry, that's a oops, that's a little mistake on me here. So actually this was incorrectly written. This means p divides n factorial minus 1. Okay, so now I can continue. Sorry about that. So now compared to this fact, what we just derived contradicts to this one, because p divides this number minus 1, then it should not divide the number that's this number. So p divides a, then p does not divide one more than a, right? If p divides this guy, p should not divide one more than that guy, which is n factorial. So this when I say this, like this fact, these two contradict to proposition 4.8.3. Okay, so that means this cannot be true. So therefore p is not true, right? It's not true. Therefore p has to be greater than n. So now p greater than n. Do you see that we already established this result plus this result? So therefore p is less than n factorial greater than n. That will be the just a little extra to finish a correct proof.